So, welcome to week 10 of live session tutorial for oral in NPTEL-SWAYAM. So, this week we'll go through hierarchical reinforcement learning. So, basically, hierarchical reinforcement learning deals with when you have um, some problems where a problem can be broken down into smaller subproblems. So, if you have a problem which can be broken down into smaller subproblems. That is when you try to use hierarchical reinforcement learning. So instead of learning the same thing again and again and again, you learn it one time and then you move on to the next mission so that you can learn it again. So basically, hierarchical reinforcement learning has a notion called temporal abstraction. So what does this mean is that each subproblem has different notion of time. So each subproblem can take different amount of time to be solved, and each subproblem could have could be could vary in the size length very vastly. So you could have a subproblem which is very small, and you could have a subproblem which is very large. So there is this notion of temporal abstraction, but where is the hierarchy? But where is the hierarchy in temporal abstraction? So the hierarchy is how you break the subproblem. And which subproblem follows which other subproblem is where you have the hierarchy. Suppose, let me give you an example. So one example would be of a grid world. Where you have 4 random locations where you can pick the customers from 1, 2, 3, 4. So the states 1, 2, 3, 4, they are source and destination states, and you have a green state which is known as the fuel state. So state F is the fuel state. Now suppose you have you are a taxi at one of the states. So once an episode of this grid world starts, you basically have the task of, so once an episode starts, a customer is randomly generated at any one of the states, either state 1, 2, 3 or 4. So suppose at this point for one episode, a customer has generated state 2 and he wants to go to state 3. So basically what you need to do is you need to pick the customer up from state 2 and go and drop him at state 3. Given that you have sufficient fuel to to go to state 2 and drop him at state 3, now you need to decide whether you need to fill up fuel in the middle or not. So this whole problem of picking up random customer at random location and dropping him off at random locations uh, under the condition that you have enough fuel could be divided into basically learning 3 hierarchical steps. So the 3 hierarchical steps are: pick a customer, drop a customer, and fill fuel. These are basically the 3 hierarchical tasks you have. Like this could be divided into these 3 hierarchical tasks. So as you can see, for our previous methods where we used, the underlying MDP was just the states, and the actions would be go up, go left, go down, or go right. And once you reach the fuel state, it would you would fill up your tank once you reach the fuel state, and then you would come up with an optimal policy for each state at where you are. But now, since also you have a notion of how full your tank is, like do you have enough fuel to go to point B, so your state also would include, with the state at which you are, would also include how much fuel you have. Yes, and yeah, so these are hierarchical. So if you know how to pick a customer, so picking a customer would actually involve you to go through the basic actions of going up, down, left, or right. But how do you learn to do that is what the first like that is the first step. Like first learn to pick a customer, then we'll learn to drop a customer, then we'll learn to how to fill up fuel and when to fill up fuel. So this is one of the basic example for hierarchical RL. So one more example for hierarchical RL could be a similar problem when I have a grid world, and now I have obstacles. So I have obstacles here and here. So I will call this room 1 and this room 2. So there are basically 2 entry doors, go from room 1 to room 2. My final state, goal state, is to reach this goal, and at each point of time I am randomly generated in room 1. So my episode starts with the agent randomly generated at any state in room 1. So now, instead of first going to the goal, my first state action, like my first hierarchical sub problem of solving the problem of going to the goal could be go to room 2 and then go to goal. Goal being that goal. So first, instead of now we'll solving for the first problem would include, so you would get an optimal policy of, so you could use any basic value iteration, you will converge to uh, this type of policy. Where you get an optimal policy which is given by so so this is one of the optimal policy. As you can see, like you trying to go through door 1 or door 2. But this is not the whole problem. No, you're not yet reaching the goal. The sub problem that you're trying to solve is going to room 1 from room 2 using just the 2 doors which are like avoiding the obstacle and using just the 2 doors that you have to room 2. Now, once you are in room 2, your optimal policy would be, once you are in room 2, the optimal policy would be to go up. Instead, go up, you'll reach the goal. So, now as you can see that, yeah, we'll come to it later that does solving for optimal policy for both the sub problems give you an optimal solution or not in the whole problem, or are you stuck with some suboptimal problem when you divide your whole problem as suboptimal problem? That will come back to. But yeah, so first let me give some uses of hierarchical reinforcement learning. So hierarchical reinforcement learning, since you are learning it sub problems, that sub problem could be used else like in some other problem which your agent is trying to learn, and so that is called as transfer or reusability of the subproblem. So what you learn is, you learn to solve an small problem or a subproblem which is not the total problem. Now you can use this subproblem to solve other problems not related to the original problem. So this has very much similarities to planning, because in planning you know what the starting goal is and what you need to do, what the end goal is. So you go from start to end, you apply some set of rules, you follow an algo, you go from start to end, you say that you are done, or you want to find some optimal way of going from start to end. So you come up with an algo to go for an optimal way to go from start to end. But in RL, you don't know what is the end point for the agent. So you need to use reward functions to learn what the end point is. So similarly, while doing hierarchical RL instead of hierarchy planning, what you do is, for each subproblem, you give a reward function and then make it learn using the normal methods which we have done till now. So in this example, a reward function of -1 for every state and plus 20 or plus 10 for reaching room 2. This reward function could help you solve subproblem 1, which was going to room 2. So now you know, given this kind of setting, how to go into other room. But this might not be optimal for the whole RL problem. We'll come back to that. But yeah, so this is your reward formulating for your hierarchical RL, and this differs from hierarchical planning, because hierarchical planning, you know what the end goal is and come up with an algo so that you know where you're going. But here you're learning how to solve the subproblem, which is generated from your original problem. So, next we'll talk about type of optimalities. So here, what do I mean when I am optimal? So I'll use the same example. So here is your board. This is your room 1 and this is your room 2. So now, as in previously, like now your original problem is to reach goal. So this is your goal. Given you start at room 1. Now, yeah. So this could be divided as subproblem 1 and subproblem 2 as reach room 2 and then reach goal. So now we'll look at optimalities, what different type of optimalities. So first we'll try to come up with an optimal policy to solve the subproblem 1, which is given that you randomly generated room 1, how do you reach room 2? So this we have seen before. So the optimal policy for this would come out to be something like this. And the optimal policy for you would be this. So I've come up with optimal policy for state for subproblem 1, and I've come up with an optimal policy for subproblem 2. But you can see that when I combine these two, this is not the optimal policy that I get. When I combine these two optimal policies, it is not the optimal policy for problem 1. So this type of optimality is known as recursively optimal. Because what you are doing is you are optimizing for each subproblem. So what you do here is you optimize for each subproblem. Now why is this not optimal is because if you are in these three states, you could pick an action of going this way. Then the most optimal action was to go this way, where your rewards are -1 for every action and +20 for each year. Okay. So if you see the optimal policy that was for B1, you could take a case where it went around door 1, but when actually the optimal policy was to just go. So now these policies are called as recursively optimal, where you optimize for each subproblem and you don't care whether it is optimal for the larger problem. So now the same thing could be done by so now you could change the policy for first by if you change these policies of just allowing them to go from the door 1, as you can see here, then allowing them to go through door 2, because in the first subproblem you didn't care whether you went through door 1 or door 2, you just wanted to reach room 2 where the goal is. Now once you have reached room 2, you wanted to go to the goal, but the optimal policy for reaching room 2 might take you to a solution which actually takes more time to reach the goal, so which doesn't search through policies which follow the hierarchy. So now I've generated a policy which searches through the policy for hierarchy, and this is known as hierarchical optimality. So this is basically you search through the policies and also follow hierarchy, and like you follow hierarchy and you also try to come up with an optimal solution for the whole problem rather than coming up with optimal solutions for both the subproblems. So there is another type of optimality known as flat optimality. So this flat optimality is basically the global optimal solution. Which does not respect hierarchy. So while getting into the rewards that you get for each optimality, so basically if you have a flat optimality policy, that is the best you can do, because that is the global optimal for your global optimal policy for your whole problem, not the subproblem. So it will be greater than or equal to hierarchically optimal. Now for this case, for this example, the hierarchical optimality is equal to the flat optimality. But if you do some changes to the grid world, then you could make different hierarchical optimality and different flat optimality. So flat optimality will always be greater than or equal to hierarchical optimality. Hierarchical optimality is optimal policy is not that those policies which follow the hierarchy and also try to come up with an optimal solution for the whole subproblem, for the whole problem, not just subproblems, which is always greater than or equal to recursive optimal policy. So recursive optimal policy is the policies where you just try to find the optimal policies of the subproblems of a problem, not the whole problem, just the subproblems. So suppose, so finding the optimal solutions for the subproblems does not imply that you have an optimal solution for the whole problem. Example here. So you have an optimal solution, optimal policy for subproblem 1. You have an optimal policy for subproblem 2. But as you saw here, that those two optimal policies combined did not give an optimal policy for the main problem. So these three are basically the types of optimality that you can get in hierarchical reinforcement learning, and your policy would be one of trying to find one of the so you would be trying to find a policy based on one of the three optimalities. So either you'll be trying to find the global optimality, like the best that I can do, or you could find a hierarchical optimal policy where it follows the hierarchy, like it tries to be an optimal solution for the subproblem 1 and also subproblem 2, keeping in mind that the subproblem 2 needs to go to a goal. Recursive optimality is blindly you find an optimal policy for subproblem 1, find an optimal policy for subproblem 2 and combine them, which might not give you a global optimal policy or a hierarchical optimal policy for the whole problem. I hope this is clear. So next we'll move to semi-Markov addition process. So we know about MDPs. So MDPs are Markov addition process, which have some form of Markovity in it. So basically what happens is, so you have state ST, you pick action 80, you go to state ST plus 1, you pick action 80 plus 1, go to action ST plus 2. So this is a MDP. So where you have the probability transition matrix as probability transitions as S prime here S comma A, and so you have all these values of S comma A in the probability transition matrix, and then your rewards are expected, or you get the reward RT plus 1, which one expected reward RT given ST comma A. So here, as you can see, the transitions for the next state at time t plus 1 depends on the state you are at time t and the action you've taken at time t. So there is only one time step dependence on this thing, which is the strong Markov property. So that is why the name Markov addition process. Now in semi-Markov addition process, SMDP, what happens is, so you have a state ST, pick action 80, and then it waits till time tau, a random time tau, and then you go to state S t plus tau. Now you pick action 8t plus tau, and then you wait till random time t prime and go to st plus tau prime. So this waiting for random time tau, which is a function of st and at that you have chosen. Here also similarly, we are waiting for random time tau prime, which is a function of st plus tau comma at plus tau. These all waiting times are random. These random time in the, this is just a mathematical computation of an assembly semi-computation. This would be interpreted in two ways in the real world. So one could be transition time. So what does transition time mean is, so you are in state st, you have taken the action A. Now to go to the, for the next transition to happen to state st, the whole environment takes some amount of time for it to happen. So it takes t amount of time. It doesn't happen instantaneously in the next moment. It takes some amount of time to happen. So then this whole thing is interpreted as a transition time model. It could also be interpreted as a holding time model. So what holding time model tells you is that given a state, you already fix a state action A, but you don't apply it to the environment. You wait for holding time tau, and then you apply at. Then there is an instantaneous transition from state st to st plus tau. That is known as holding time. Now, for RL, we'll be mainly looking at transition time. So we'll apply the action at time t, but then the environment to react to your action would take tau amount of time to react and come to a new state st plus tau. So this type of formulation, mathematical formulation, is known as an SMDT. So and another thing to remember is there is no continuous time, notion of continuous time concept here. Like you can bring in continuous time concept here, but these taus are natural numbers. So like take time to wait for a random positive integer time, then you transition. Then you take action t plus the positive integer time that you have waited previously. And now you wait for tau prime amount of time, positive random integer tau prime, and then you take another transition. Okay, so SMDPs can be viewed as states, the set of all states, set of actions, which is similar to an MDP. Then you have a transition probability matrix and the reward. So the transition probability matrix is given by S prime comma tau given S comma A. Whereas in MDP you had just the S prime given S comma A. Now given in S comma A, you also have a distribution of how much time should I wait or how much time does it take to transition to the next state. So this is your new transition probability transition matrix, and then your expectation is given by reward such that S A, the new state, and how much time I waited for that state. So this actually comes into play when like how much time you have waited also depends on what reward you are getting, because this will be more clear when I discuss options. So but this is how semi-Markov prediction process are already. So you can write the value function and Bellman equation for this. So I'll be writing the SMDP. Q learning update. So the Q learning update is given by Q st comma 18 is equal to Q st comma 18 plus 8.8 RT plus tau. So now what? So what is the meaning? So since to go to the next state, you have waited till tau times. So what this RT plus tau consists of is all the rewards that you have gotten till t plus tau, and then plus gamma power tau x where your rt plus tau is equal to rt plus 1 plus gamma rt plus 2 plus gamma square rt plus 3 plus so on, not or minus 1 r plus tau. So once you're in state ST, if you have an underlying SMDP, if you're not following an MDP policy and you're following an SMDP policy, or your underlying multiplication is 7 Markov, so once you have taken action 80 at state ST, you have to wait till time tau, which is random, to go to the next function, which is ST plus 1. So you update your queues once you have waited for that much amount of time, and then you update. So how does this play a role in hierarchical RL is? So here now your actions would just be the subproblem 1 of reach room 2. So once you are given a state, you take all the actions, you complete one episode of reaching room 2. Once you have completed reaching room 2 for some policy, then you update all the queues that you have seen based on this SMD. So it will become much more clear when we go to options, like we are defining options. So now we will talk about options. So options are basically macro actions or a set of actions combined together. And like options are short policies for your subproblems. So mathematically options have an initiation set, the subset of your state space of your original MDP. So what this tells you is, what this tells you is the initiation set is you can't take a set of actions from each and every state that you are in. So you need to limit yourself. So if you are in one state, the length of your actions, the number of times, the number of actions you take to your state is very reduced. So as seen in this problem for when you're finding out optimal policy for hierarchy RL. So if you are in this state, so just one action you are done. So now if your option had a set of 2-3 actions, like go up, go left, go right, go left, then it would not matter if you have taken the action here, because you'll hit into an obstacle and it makes no sense. So there are some states where you can initialize your options from, and for each option you will have some sets where you can apply the options from. So that is the initiation state for the option. The next one is the policy. So policy pi of an option, basically if you have a state, it gives an action, or it could also be if you have a state, it gives a set of actions. So now if you are at state 1, if you, instead of applying an action, if you apply an option, what the option would do is go through all these actions, and after going on through all these actions, it will look at what state I am in after t plus n. So this is similar to the SMDP, where I take a state, I take an action, I apply the action on a state, wait for tau time, and then transition to a new state. Similarly, what an option does is, given a state, it takes an option, it applies multiple actions which you are agnostic to. You don't care of what actions it does apply. You wait for n time, and then it reaches to a new transition state. Now you see that, okay, what is the total reward I've got during these n steps, and what is my new state. Next is your termination. So termination is if you can end up in a state if you choose an option. So one of the most basic similar small example for like there are 2-3 examples in the chessboard. So as you can see, you have the bishop. There is a white bishop and a black bishop on the chessboard. So the black bishop will always stay on the bishop. They go diagonally in the chessboard. They don't go any other way. They can just go diagonally. So for a black bishop, the initiation states would just be black states, because it can't ever go to a white state. Even termination states would be all the black states. It can't never go to a white state. So the I0 for a black bishop on a chessboard is basically all the black squares, not the white squares, but it can never go to white square. Now the policy for black bishop could be, so it wants to go from one black square to another black square. So the policy for a black bishop could be go diagonal right 3 steps and go diagonal left 3 steps. It could reach some. So first action would be to go diagonal left. Next action should be go diagonal right. Next action could be go diagonal left. This is it. So it could be anything. But it would always, with probability 1, reach a black state, because a black bishop can never go to white state. Similarly, for a white bishop, it would be the other way around. So all the initiation states would be the white states, and all the termination states also would be the white states. So now the bishop is one of the examples for an option. The next thing is you have a horse. So horse can only move 2.5 steps. So 2.5 steps. Or is it 1.5 step? It's 2.5 steps. So a horse can move in this manner. So now, this also could be modeled as a semi-Markov process, because once you move a horse, you know you can never terminate at this state. So your actions would be to go up 1 step, go up 1 step, and then go left 1 step. And then you stop, and then you reach a new state. So the initiation states also differ for horses, and given on what initiation states you have for the horse to start taking your option here being go. So now horse has 2 options. So option 1 is go up, go right. And option 2 is go up, go left. So now you have set of actions together with you, which you can form as an option, and then that could be a semi-Markov process. Okay. So we are done. So now there are 2 type of options. So one is a Markov option, and one is an SMDP. Okay, so as I told here that for a option it could be pi 0, given a state you give an action, one action, that is a Markov option, which is basically just your policy for your actions. So this we have looked into many, for all these days we have been looking through just the Markov options, which is another name for policy. So you want a policy given a state, you want an action. So now so now we are trying to look at for semi-Markov options. So now semi-Markov options, instead of once you are in a state, instead of giving one action, you give a whole array of actions. So now you want the whole array of actions such that you can formulate it as an assembly. And here, so what happens is, okay, so maybe I should go back to the variable. So suppose a smaller grid one. So if you start here, and now your option is to go up, and left. Okay, I can't go up if I start here. So see, I run into problem because up, there is no up actually. So the state that I am in is not an initiation state for this option. So I can't use this option. So maybe I will change the option as up, left and down. That is a valid option for this state. So I go one step up. Now what happens is, what action I take in this state depends on what option I have taken in this state. And what action I take in this state also depends on what option I have taken in this state. So there is a two second order Markov. So it's basically, it's not just immediate history which Markov does, but it's 2 times the previous. I need to remember which state I had taken the option, so that I can take the action in this step as coming down here. So now instead of having Markov decision process as our underlying this thing, we are having semi-Markov decision process. So now, so basically your options are, so how can you define your options are? So given an option, I have the initialization states from where say this option, where all can I initialize? I can't initialize in any of these 4 states. I can initialize in these 4 states, and I can initialize in these 4 states. I think I can't do it here also. So this is my initialization state for this option. And termination states depends on those options, and you take those states and you end up. So once your initialization states are fixed, the termination states are fixed. And the set of actions, pi 0. So pi options would give me 3 actions, these 3 actions as these choices. And the termination state. So the termination state basically it fixes, but sometimes what you have is, since you have stochastic, so this could be stochastic. So it could be okay, with probability 0.7 go up, with probability 0.3 go left, like in the first step with 0.7 go up and 0.3 go down, and then with probability 0.7 go left, 0.3 go right on the second step. So since this could be a the option could be a stochastic policy, we are dealing with deterministic policies now. So your betas could also be a distribution on the states, as to it points out that with what probability you'll end up in this state, with what probability you'll end up in that state. So there is that information also. So that is why we keep the beta naught, because in deterministic, once you fix the IO, your beta naughts are fixed. So what is the even point of giving beta naught? But the point of giving beta naught is, if your policy is stochastic, your options are stochastic, your policy on options are stochastic, then instead of getting the same fixed state, you could get a distribution of the states. Like if you start at this initialization states, with what probability I will end up in a new state. Okay, so yeah, so learning with options. So basically you are updating S. Instead of now actions, you have options. So once you start at state S, you have to update with option O. So what happens is, so now you have pi O, which states you take A1, A2, so on till AN. So because of this, you have S1. So I want to update S1 comma S1 comma S2, so on Sn. So now I can update Q of S1 comma A1 as Q of S1 comma A1 plus alpha into R1 plus gamma max Q of S2 comma A minus Q of S1 comma A1. So basically what this is telling is, applying option from state S1, because you know that the first step of option is applying action A1, is similar to updating the Q function for S1 A1 pair. Similarly, you can update S2 A2 pair, because you know that the option is set of A1 to AN variables and so on. You can update to Q of SN AN. You can update these things. This is the more underlying. So here base hierarchy comes in. You have primitive states, primitive actions. Now you are hierarchying. Now instead of wanting to do it over all the actions, you want to do it for a sub-problem. That sub-problem contains those options, such that you have a series of actions. Given that you have that option of choosing the series of actions, you can go to state 1, choose the option, so that it does all the actions for those states, and since you know what the actions that options choose, you can update all the Q functions for S1, A1, S2, A2, so on to Sn, An all at once. So here comes why learning hierarchically is good in some problems. Okay, I think most of you have guys learned it. Do you want me to give a quick recap of what I have done till now, or do you want me to go on? Because I think I have 5 more minutes. So you guys want me to do a quick recap in the for the last 5 minutes, or yeah, okay, I'll give a recap. Sure. Okay, so basically today what I started with was hierarchical reinforcement learning. So in hierarchical reinforcement learning, what you do is you take a problem, instead of solving the problem, you break the problem into sub-problems, and you solve for the sub-problem. And once you solve the sub-problem, you're like, okay, I'll go into the next sub-problem, I'll solve the next sub-problem. So hierarchical reinforcement learning basically have temporal abstraction. Temporal abstraction means that each sub-problem could be as big as possible or as small as possible. So there could be a sub-problem which is very small. So now suppose, I'm in my room, I need to go from here to a restaurant to have my food. So one of the sub-problem could be, okay, I need to learn how to reach my door, the door in my room. If I don't learn how to reach my door, I'll never reach the restaurant. So one of the sub-problems of reaching the restaurant is going to my door and opening my door. So that is one sub-problem. Going to my door and opening the door could be very small sub-problem compared to from this door going to the main gate of my hostel or something could be a bigger sub-problem. So temporal abstraction is each sub-problem could be as huge as possible or as small as possible. But the whole notion of you breaking up the bigger problem into smaller chunks, so that what happens is, suppose now I have a different problem. I don't want to learn to go to the restaurant, but I want to learn to go to how do I go to my lab. So if I want to go to my lab, the sub-problem of me going to the room remains same. So I need not learn it again. I hope that is clear. Okay, so how does hierarchy come here is, the hierarchy here comes in how you break the sub-problem. So wanting to learn to go to a restaurant involves first me learning to go to the door in my room. If I don't learn that, I'm never going to the restaurant. So the hierarchy is, unless I learn how to go to my room, I can't do the next thing. So next what I gave is, I gave a small example for hierarchical reinforcement learnings. So this is a grid 1 where you have 1, 2, 3, 4 as random locations where customers could randomly pop up, and their destination could randomly be one of those 4 states. So now you are a taxi driver and you have limited amount of fuel in you. So your state space would be the grid 1, which block you are, and the amount of fuel that is there is in your car. There is this green block. That green block is fuel refilling station. So now this thing, once an episode starts, so episode starting is you generating at a random spot and a customer generating in random 1, 2, 3, 4, any of these 4 states. So then you need to learn how to pick a customer. Once you've picked a customer, you also need to learn how to drop a customer. And you also need to learn how to fill fuel. If your fuel is empty, you need to make sure of that also. So the whole subproblem of picking customer and dropping it and making sure that your fuel is filled depends on these 3 problems: picking up a customer, dropping a customer, and filling fuel. So if you can solve the problem of picking a customer and then dropping a customer and then filling fuel optimally, you have basically in a sense solved the whole big problem. Yeah, so there was this another where I showed that given a room 1 and room 2, your agent randomly generated state in room 1, he needs to go to room 2. So you do it separately, like you find the optimal solution for going to room 2 separately, and then once you are in room 2, find the optimal solution to go to the room. So this is what you get. So next there were 3 types of optimalities for hierarchies. So what it basically tells you is solving for optimal subproblems. So now you have suppose 2 subproblems. You have got the optimal policy to solve the first subproblem. Got the optimal policy to solve the second subproblem. Combining those 2 does not imply that you have an optimal policy for the whole problem. This is clear. So when you solve for optimal subproblems for each of the case, that is known as recursively optimal. So recursively optimal is you are optimizing for each subproblem. But this does not imply that you have optimized for the whole larger problem. So hierarchical optimality is you search to the policies and also follow the hierarchy. You see that whether the sub-policies that I have generated for both the problems, when combined together, give me a optimal policy. So hierarchical optimality is better than recursive optimality. Flat optimality is straight out, it does not respect hierarchies, it just solves the global optimal solution for this. The global optimal solutions. It doesn't respect the hierarchies. So for this problem, the flat optimality and the hierarchical optimality are the same, but you could do some small changes, like you could add fire in this block and then don't allow them to go here but allow them to go here, but then that does not take care of hierarchy and all, but that will take some time for me to explain. So basically what happens is your rewards that you get is for flat optimality, which is the global optimal solution, you'll get the highest amount of reward, which is greater than or equal to hierarchical optimal. Hierarchical optimal, it satisfies the hierarchy, but it does not mean that you have it satisfies the hierarchy, so it's optimal for the whole bigger problem as well as suboptimal problems. They are suboptimal. Recursively optimal policy is you've gotten a policy which is optimal for subproblem 1 and optimal policy for subproblem 2. But when you combine these 2, they did not be the optimal policy for the whole bigger problem. So recursive optimal policy gives you the least amount of results, least amount of reward, then hierarchical, then flat optimal. So then I went into semi-Markov relations. So SMDPs were basically MDPs but with random transition times or holding times. So these usually played a role while solving these subproblems. Okay, so solving these 2 subproblems. So this subproblem could take a different amount of time and this subproblem could take a different amount of time. So coming up with these options, coming up with those 2 things, you need to define options which uses SMDP. So options are basically MDPs plus so SMDPs are basically MDPs plus options. So now instead of looking at each state and action, what you do is you look at state and a whole set of actions. So you wait for n time steps and then you see where you pop up. similar to a chess bishop or a horse or whatever you want. So now your queue learning becomes a bit simpler because you take one option, given a state, you pick an option, it goes to n steps, you update each queue function for S1A, S2A, S3A, SNA. You do this multiple number of times, you will converge quickly for evaluation. This is how you learn the options. So if you guys have any doubt, you can ask. Right? I think I will start.
I have one doubt with respect to the optimalities. So the blocking conditions are clear for flat optimality and because of the optimal policy.
Yeah, yeah.
Whereas it's not that clear for hierarchical optimality.
The stopping
Flat
condition.
optimality, we just don't divide it into sub problems and we just take it
Yeah.
as a whole problem
Take it
and
as a whole problem. Yes.
disregard hierarchy.
Yeah.
And do, say, for example, let's do policy.
Yeah.
So you get the optimal policy.
Yes.
And then for recursively optimal, you apply policy iteration for
Each of the
subproblems, and you get
subproblems.
you get optimal policy for each of the subproblems.
Yeah.
Whereas you can't decide where to stop for hierarchical.
Yeah, yeah, yeah. Yeah, so, but you know that hierarchical optimal policy lies somewhere between the flat optimality and the recursive optimality. So, one of the stopping conditions for hierarchical optimality could be like, instead of coming, so you agree that there could be multiple optimal policies for one subproblem.
Yes.
So, I hope you have gone through such lectures for the optimality conditions, right? So instead of searching for one optimal policy, you have to search for multiple optimal policies which could pop up from those, and then you need to put pairs for the multiple optimal subproblems and see which gives you a higher reward. So anything which gives you a higher reward for multiple. So what I'm saying is hierarchical optimality would be suboptimal for your subproblem. Could be suboptimal for a subproblem. So instead of finding just the optimal policy, find all the suboptimal policies on one subproblem and try to pair them up and see which gives you the highest. Once you pair all of them up, you do I think a sort on the rewards for these things and come out as your hierarchical optimals. But anything which is better than the recursive policy and satisfies your hierarchy is an hierarchical optimal policy. I hope you see that.
Okay.
Does it answer the question?
Yes, it does.
Okay. Any more doubts on similar?
Say for the chess example that we gave, it seems like chess is example. Say with the bishop, right? So we need few function for each of the pieces.
You need few.
Each of the pieces using XMPP, right?
I didn't get you. You need
Few functions.
You need queue functions. Yes, you're absolutely right. Queue functions.
Yeah, for each of the pieces, right?
For each of the pieces, yeah. Like now these could be, you could get this optimal policy from value iteration also will converge to similar things. From Q learning also will okay. Q learning you might converge to different Q and SARSA you might converge to different things. But those all will be suboptimal in some sense for subproblems.
Yeah.
And here it's yeah. Go ahead.
Hey, go ahead. I don't have anything to say.
Huh?
I don't have anything to say. Just please continue.
So no, you were asking something. Yeah, go ahead. I forgot what I was going to say.
No, since we have Q function for each of the pieces,
Yes.
It would be kind of inefficient and let's say we are tackling a chessboard problem, right? So have a Q function for each of the chess piece.
Yes, yes. So inefficient in
So
the
I
sense
told
that
that
it would
it
not
is.
it would not be optimal. So you're trading off for optimality and transferability. I think that is the. So
Okay.
so is that what your question is? I didn't answer the question, but I was thinking that yeah, it would not be efficient. You're right. But now you have so now suppose the goal changes in room two to something else. You don't need to relearn your whole problem of room one.
Hmm.
Suppose now you don't know
Right.
about the room
That
one.
was also one question that popped up when Sir was teaching hierarchical model. So we are more we are using options, right? Say
Yeah, yeah, yeah.
some sub option of that particular some subsequence of actions from an option
Mm-hmm.
can be used somewhere else if you encounter the same problem,
Yeah,
right?
yeah, yeah.
So how do you take that subsequence of actions and put it there? Because the idea, the way I understand hierarchical RL is that you have a black box in which you put a subproblem and then comes back with a sequence of actions.
Yes, yes,
So essentially identifying subproblem from that black box, which
yes.
can fit another subproblem, will be difficult, right?
Yeah, that will be difficult. Yeah, I think Sir mentioned in one of his class also, like, how do you come up with options? That is a whole research going on. How do you come up with options? But given that you can break your problem into hierarchical option wise, you can make sure that you can go to some optimal policy. You can come up with some optimal policy by designing them as SMBs. Like that is the whole goal. But now, given a problem, how do I come up with what options fit in that problem? That is something the domain expert or the guy who is trying to implement R into his domain needs to take care of. Take care of.
Okay. Okay. Okay, well, this makes sense. Right. There was one question not related to RL. With the previous week's assignments, couple of weeks assignments, so
Huh.
I had raised issues in the discussion forum, but it recently I didn't see any updates.
Okay,
So
I think.
is there any possible?
Okay, I think